This is our manometer. Everything is fully configurable using a variable studio. This allows a greater freedom in the design process. Now, let's look at our manometer. It is composed of the base, the modular brick, and the tube mounting adapters. We use an outer diameter of 5/8-inch tube, and since everything is configurable, I can simply change my variable studio so that it can adapt to any sort of tubing. Now, let me show you how you can be a genius by deriving your own formula. Since pressure equals force divided by area, and force is also equals to mass times gravitational acceleration, and density equals mass divided by volume, which also turns to mass equals density times volume. Now you can achieve this equation. But wait! Volume equals length times width times height, and area equals length times width. Then volume must be area times height. Then therefore, pressure equals density times area times height times gravitational acceleration over area. Can't you simplify that? Aha! You're a genius. Congratulations, you invented the hydrostatic pressure formula. We're assuming that the initial ATM is 1. So how do we convert from the height difference to our pressure? Well, 1 centimeter equals 1/100 meter, and 1 PA equals 1/1000 kPa. Then we can get that 1 centimeter of height difference equals 98 PA, which is 0.09 kilopascals. Since the Kempty law states that the pressure is caused by random moving particles acting on the wall, then if gas molecules collide more frequently, then pressure should increase. Now, if we look at the Gay-Lussac's law, assuming volume is fixed, if the temperature increases, then the molecule moves faster, which corresponds to an increase in pressure. And also it can be explaining ideal gas law, which the temperature causes an increase in molecular speed, which results in an increase in pressure. Here's an iconic example where as the flask reaches a cold water or cold ice, the pressure went negative and reaches the opposite end. And here is another obvious height difference. Sadly, we realized a major problem during our calibration process, which is that the internal temperature is not corresponding to the external heat pad temperature. And you can see the temperature is fluctuating between 60 degrees Celsius and 120 degrees Celsius. And we kind of mess up. Another problem that we face is that our initial water level wasn't sufficient enough for it to reach a higher height level. As you can see, bubbles start to form as air starts to pass through. Another thing is that we did not obtain a greater range. As you can see, our tube was not enough for this temperature change. And unfortunately, we kind of burned some wires. We don't want to do that in rocketry for sure, as manometer is used to measure the pressure of liquid tube for. Anyway, like and subscribe if you like the video.